Hello and welcome to this video looking at how we use the chi-squared test. So the chi-squared test is a statistical test and it's designed to find out if there's a difference between observed and expected data, and it's to see whether the difference between them is significant or whether the difference is just due to chance. So we would have a null hypothesis so that we could accept that based on some results, but we'll go into that later. So there is some kind of things that we need to consider when we're going to use this test, and there's some requirements that are the data needs to be in categories, so it needs to be continuous data. Oh, sorry, not continuous. Can't be continuous. So it's got to be in categories. So, like, earlobes are either attached or not attached. You're either blood group A or blood group B. Do you know what, like that kind of thing? And there has to be a strong biological theory to predict expected values. There needs to be a biological theory. The sample size has to be large, so we've got a large sample size, so we can say that something is representative. The data is only raw counts, so percentages, ratios cannot be used, so it's like whole numbers really. And there are no zero scores, there cannot be any of those, so no zero scores. And they are the main ones. So I think I'm going to do this. I think it'll work best if I go through this as a worked example. Okay. So if we're looking at mice colour, mice coat colour, the dominant is capital Y dominant, and that is for yellow. Lowercase y recessive for grey. So if we have the genotype of a grey mouse, we would say that the grey mouse is lowercase y, so it's homozygous recessive. And if two heterozygous yellow fur, so we know that's YY, crossed, they produce, if this was given in a question, it would say that give, say, 140 yellow and 68 grey mice. So what we need to do is we need to find what our expected value is, and we can use this doing the genetic diagrams. So we know that two heterozygous yellow furs cross, so we can put this in a little diagram to find our expected values. We know that capital Y, lowercase y, capital Y, lowercase y, y. So we know that we would expect 75% of the offspring to be yellow, and we'd expect 25% of them to be grey. So now what we need to do is, so the expected ratio should be 3 to 1. And now I'm just going to write the equation up here. So x squared equals, this just needs the sum of O minus E all squared divided by E. O being the observed value and E being the expected value. And this is probably best put into like a table so that your working's out a lot clearer, especially if it's in the exam for a marker. It would be a lot easier to do like that. So we know our ratios and now we know our expected. Like this. So put it in a value, we've got expected value. So we've got 208 mice in total if you add this 68 and 140 together. We've got 208 mice. So we do 208 divided by the 4 different offspring equals 52. And this is the 25%. If you times that by 3, you get your 75%, which is 156. So our expected value for yellow is 156, and it's 52 for the grey. Okay. If we're looking at the observed value, we observed 140 yellow. We observed 68 grey. We need to do O minus E. So 140 minus 156 minus 16, 68 minus 52, positive 16. Then we need to do O minus E squared, which is 256. Same for this, it's 256. And then we need to do O minus E squared divided by E, which is a full, so we're just deciding. So we've got this number, 256, divided by 156 is 1.64. 256 divided by 52 is 4.92. And then what we do to find x squared is we add these two numbers up because it's the sum of, and that equals 6.56. All right. Clear a bit more space on the board. So now we've got, this is x squared, we've got this here. Don't be tempted to square root it. X squared just is a symbol for chi-squared, so we don't need to square root it, leave that as it is. Now we need to find the degrees of freedom, and that is always the n minus 1. In this case, we've only got two options of phenotype, grey or yellow. So it's going to be 2 minus 1, which equals 1. So our degrees of freedom equals 1. So we find the critical value at 0.05 level of significance. And for this, at 1 degree of freedom at 0.05 level of significance, the critical value equals 3.84. So what we can say now is that our calculated value of 6.56 is larger than the critical value. Therefore, the difference between the observed and the expected value is not due to chance. So must be significant, therefore we reject the null hypotheses. So the null would be, the null hypothesis would be there is no statistical significant difference between the observed and expected data. Any difference is due to chance, but we're rejecting that because it is significant. And that's how you calculate the chi-squared. Just so you know, if the if our calculated value for x squared was lower, for example, if it was 2.46, for example, then we would have to accept the null hypotheses, and the difference between observed and expected would be due to chance. Thank you for watching.